That's right. Yeah. Thank you so much, Jim. Thank you so much for having me. It's an honor to be here. Oh, yeah, sure. I'll take care of it. It's a good thing. Can everybody hear me okay, by the way? Okay. It's a good thing that none of you are astronomers, because that means I can make up anything and you'd still believe me. Is this too dark? Is this okay? Okay. All righty. Okay. I want to take you on a little tour, a history lesson, if you will, from the early 1900s up until today, this year, 2025, because in the last 100 years, we figured out, one, that the Milky Way wasn't the only galaxy in the universe. Two, the universe is expanding. And three, we can measure how fast it's expanding. And then we figured out, well, we can measure it, but there's more than one way to measure it. And those two ways of measuring how fast the universe expands don't agree. And the better that we get at our measurements, the more and more they don't agree. So I'm sorry, I'm going to spoil it. I'm going to leave you on a cliffhanger today, but hopefully it'll garner your interest, and maybe when an update comes out, because there's an update about this topic every week, it seems like, it might catch your interest, and you might even read an article or two. So our story starts all the way back in the 1920s with who my students know as the godmother of extragalactic astronomy. This is Henrietta Leavitt, a very cherished person in the history of astronomy and astrophysics and our learning about our place in the universe. She was one of the original Harvard College computers under a scientist called Pickering, and she was assigned to study stars that look like the star that you're seeing right here. Now, this isn't a real picture of a star, this is a simulation, but it is a stellar evolution simulation. There are physicists in the Department of Georgia State University that are very, very good at modeling the interiors of stars. So good, in fact, that the stars that we make in our simulations look as similar to stars in the real world as they ever have been. So what kind of stars was she looking at? She was looking at stars in one of the dwarf galaxies that's orbiting around the Milky Way. The large and small Magellanic Clouds are the largest dwarf galaxies. She was looking at stars in the small Magellanic Cloud. And she was looking at stars where every time that she would look at them, their apparent brightness, as measured from Earth, looked different. What we now understand is happening is that these stars are called variable stars, where normally stars like the sun don't usually change their dynamics because they're in a state of what we call hydrostatic equilibrium, where the enormous mass of the sun is trying to pull everything inwards, and it would had it not been for the nuclear fusion that's going on in the core. That's smashing hydrogen atoms together, producing helium and a whole host of energy, and all of that energy tries to radiate outwards in all directions. So the pressure from the radiation caused by fusion pushing outwards exactly balances gravity that's pushing inwards. And so you have two competing forces that keep stars the same size. If they're not able to reach equilibrium, then the interior of the star will swing between the radiation pressure being really strong and fusion being really strong, and then gravity being really strong, and then fusion being really strong. The inward force and outward force start trading who's winning, just like us, just like our football teams. So when the gravity is winning, the interior of the star will compress. If you compress a gas, you increase its temperature, you increase its pressure. If you increase the temperature of a gas, you are increasing the average speed of all those particles in that gas. And the faster particles move, the more particles are going to be able to fuse. So if you increase the temperature, you increase the number of particles that are fusing, which means you crank up the amount of radiation pressure by compressing the star, which means radiation pressure goes up, it gets pushed outwards. The star expands, and expansion cools off the gas, radiation pressure cools down, gravity starts to win again, the star compresses again, which fires up the oven inside and increases radiation pressure, which expands the star, and over again, the star will be expanding and compressing and expanding and compressing. The color is also changing here too, because, as my students are now repeating to me in class, blue is new, red is dead, blue is hot, and red is not. So if you increase the temperature of anything in the universe that produces its own light, it will turn bluer, and if you make it even hotter, it'll turn ultraviolet, and then X-rays and gamma rays and so on and so on. And so if these stars take huge swings in temperature, then they really will swing back and forth from looking big and small, looking blue and looking red. When the star is bigger, it will look brighter to us, and when it is smaller, it will look dimmer to us. There are a couple of kinds of stars that do this. Henrietta Leavitt was studying the most studied version of these types of stars, which are Cepheid variable stars. This is a scan of one of her original photographic plates from the Harvard College Observatory photographic plate collection. What you're seeing here is a plate of glass with an emulsion on it that will change color if a photon hits it, just kind of like film stock, filming on actual film instead of on digital. So this little blob is the Small Magellanic Cloud. That's just a little collection of gas and stars that's orbiting around the Milky Way. And all of these are her notes and labels for every star that they detected as a variable star. And so they repeated their observations and tracked how the brightness of these stars changed. How fast do these stars go through one full cycle of expansion and compression? Anywhere from a couple of days to a couple of weeks. Imagine the sun getting 10 times as big as it is now and then going back to normal in the span of 7 days. That's what these stars are doing. What does this guy look like in real life? I'm an astronomer. I can't help but just show you pretty picture after pretty picture. This is what it looks like. This is the Small Magellanic Cloud as observed from the ground with a few different amateur telescopes. So, what do these stars look like in real life? These stars have become very important for astronomy, and they've become very important for the study of other galaxies, which is my area of expertise. What do they look like? Well, Hubble has seen these. This animation is going to zoom you into the location in the Milky Way. This is the Milky Way. This is the Large Magellanic Cloud. This is the Small Magellanic Cloud. It's going to zoom in, and then it's going to transition into an actual observation of a Cepheid variable star from the Hubble Space Telescope. And right there, causing the big diffraction spike, is one star, which if observed for some small period of time, you will see that star increase and decrease in brightness because it is increasing in both size and temperature. This is a real movie from the Hubble Space Telescope of that star expanding and compressing. Now that looks like ripples in water. That is not ripples in water. What you are seeing is the same exact effect of you looking at somebody bouncing a basketball really far away. You'll see them bounce the basketball before you hear them bounce the basketball. And if you're, if no one's really around, you might even hear an echo of the sound of that basketball. What you're seeing is light taking time to get places. The scale of this image is light days, meaning that if you looked at one photon cross from here to here, it would take that photon a few Earth days to make the journey. So what are you seeing? You're seeing the ripple of light from a variation in brightness go from here and then light up these clouds, then go here and light up these clouds, then go here and light up these clouds. You're seeing a light echo given by a movie observed by the Hubble Space Telescope. Here's another view of it. That's real, folks. And this was made before all of those ChatGPT things were invented, so I know it's real. I know it's real. And just because I don't have a scientific reason to show you this, but here's an artist's rendition of what this observation looked like. Clouds of gas. Our clouds of gas are made of mainly water vapor, right? You can have clouds of gas made of water vapor. You can have clouds of oxygen. It's a common one. Clouds of carbon. Mainly it's dust in the Milky Way. And so you get graphite, you get, here's your word of the day, polycyclic aromatic hydrocarbons. One of my graduate teachers will be happy that I said that. Alrighty. So she collected a sample of these stars, all in the Small Magellanic Cloud. And she said, okay, let's figure out, one, how bright they appear to us. Some appeared brighter, some appeared dimmer. And then let's measure how long they take to go through one full cycle of expansion and compression. So a period of pulsation. This is her original plot of her original results of two different stars from 1912. These are two stars where, I'm sorry, there are two stars and two different star clusters, excuse me, where this is one group of stars. Imagine one little group of stars, one little cluster of stars, and then imagine another cluster of stars that's slightly farther away. This one is the closer one. This one is the one that's farther away. Each of these dots is a data point representing one star in that cluster. On the x-axis is the time that it takes to complete one full period of pulsation. And on the y-axis is how bright these stars appear to us. And because they're pulsating, these are their average brightnesses. So astronomers are weird. Smaller numbers, if you go more towards the negatives, it's a brighter star. So brighter goes up. And what we see is that there seems to be a linear correlation between how long a star takes to complete one period of pulsation and how bright it is. These are two different clusters. We don't know how bright they actually are. All we can measure is how bright they appear to us. If you have a light bulb some distance away from you, you can tell me how bright the light bulb is, but unless you know what the voltage is, you don't know how many photons that thing is actually producing. We have the same problem with stars. But it's a good relative distance measure, because all we knew before we plotted this is that this is a cluster and this is a cluster. I have no idea if one's closer, if one's farther. If something's brighter, it doesn't automatically mean that it's closer. It might just actually be producing more photons. But what this is telling me is that these stars are brighter than these stars. And so it is a good relative distance tracker. I don't know how far any of these actually are, but I know that one is farther from the other. There we go. The discovery of these stars has become such an important anchor for our understanding of other galaxies, the scale of the universe, its expansion rate, the existence of dark matter and dark energy, that in this year, 2025, a person who is going to become very important and who's also about to become a collaborator of mine, Dr. Adam Rees, who won the Nobel Prize in Physics based on his publication in 1998, which provided the first observational evidence that the universe was not only expanding, but accelerating in its expansion rate. He had one of his, I believe, postdocs go back to the publication and the data and the measurements of the original 1912 publication of Henrietta Leavitt and tried to reproduce her results, but using the best results from the Hubble Space Telescope and from the James Webb Space Telescope. Now, there's a QR code if you want to scan it and visit the paper on your own. I just want to highlight two specific things in this abstract. One, because I think it really nails the point home of how important this woman was. And two, the writing in this is excellent and it's better than how I could word it. So, Leavitt measured light curves, periods, and minimum and maximum magnitudes from painstaking visual inspection of photographic plates. Her work paved the way for the first precise series of distance measurements that helped set the scale of the universe, and later the discovery of its expansion by Edwin Hubble in 1929. Overall, Leavitt's results, which they explored here, are in excellent agreement with contemporary measurements, reinforcing the value of Cepheids in cosmology today, a testament to the enduring quality of her work. Here's just a few examples of how good her work was when put up against, side by side, the best results, the best observations from the best telescopes that we've spent your taxpayer money on. On the left is her original plot I just showed you. These are two different star clusters and the period of pulsations that she measured by hand and the average magnitudes measured off of photographic plates that she measured by hand. And on the right, the same exact objects, but every measurement was made by either Hubble or the James Webb Space Telescope. Those are the same plot. In 1912, she was able to do something that Hubble and James Webb are doing right now. That's the correct reaction, sir. Here is a comparison, a direct one-to-one comparison. So on the y-axis, we have the average magnitudes as measured from our best surveys, minus ones originally measured by Leavitt. And so if something is on the horizontal line at 0, that shows perfect agreement. And on the x-axis is the measured period of pulsation. All of the blue stars are comparisons between their two data sets. They're all hovering around the line, which means they basically got the same answers 100 years removed and a couple $1 billion difference in technology. And all the ones highlighted in red, well, we looked back at those stars. Those stars are just weird. There was no way for her to know that those stars would behave weirdly in the future because she only had data that lasted a few weeks for all of these stars. We have 100 years of data on these stars, and so we have a huge swath of behavior that we're able to analyze that helps inform why these outliers are behaving the way that they did. So if you ignore those, Henrietta Leavitt is within a factor of 2 of Hubble and James Webb over 100 years ago. Meanwhile, in the 1920s, there's a big debate going on in Harvard. And here are our players, Harlow Shapley and Heber Curtis. What's been going on recently? Well, before this debate, everybody thought that the Milky Way was the extent of the universe. A couple hundred years ago in the 1600s, we figured out, oh, alrighty, things aren't moving around the Earth, but we want to be the center of the universe. We're the center of the universe. And then we figured out, well, those epicycles that we keep adding to the geocentric model just make this look like nonsense. So let's make everything move around the sun. That's way better. But the solar system is the extent of the universe. And then our observations got better. And we said, okay, all right, fine. The solar system isn't the extent of the universe. Our sun is a star that's hanging out with a bunch of other stars in this galaxy that we're going to call the Milky Way. But this galaxy is all there is. Of course there's not other galaxies. Why would there be other galaxies? To assert that there were other galaxies before this debate happened in the late 1920s, to assert that there were other galaxies would laugh you out of the room because we just didn't believe it. It would be a silly assertion to everybody, to the leading scientific minds back then. The problem, though, was that our observations were getting better. And if you look up in the night sky with a good telescope, sure, you'll see a bunch of stars, you'll see the moon, you'll see planets, but you'll also see these fuzzy blobs. What they called those back then was nebulae, but we understand those now to be other galaxies. And we got better and better in observing those, and so it set a precedent. What are these things? They don't look like stars. What are they? Why are they? How far away are they? Are they connected to the Milky Way or are they not? Because if they're not connected to the Milky Way, we have a problem on our hands. Because those things, if they're galaxies, if they look that small, the only logical explanation as to why something that's as big as the Milky Way, they assumed, to be that small, is it had to be really far away. How far away? Farther than anybody ever considered anything to be ever. And that sounds like a silly sentence, but that's really what was going on. And so Shapley said, these aren't part of the Milky Way. That's obviously not the case. Astronomy is hard to take serious anyways. So these things are attached to the Milky Way. They have stars like the Milky Way. They have novae, stars that are exploding like the Milky Way. Their spectra reflect compounds of gas, just like the Milky Way. It's fine. They're connected to the Milky Way. Curtis said, I don't think so, because why, when I look at Andromeda, for example, the Andromeda Nebula, which wasn't understood to be a galaxy back then, if I look at the Andromeda Nebula, why am I seeing a different rate of stars explode in that location than I am anywhere else in the Milky Way? Why would one part of the Milky Way have a completely different evolutionary history about those stars in that region compared to anywhere else? And that was kind of it. The debate wasn't settled because we didn't have enough data to lend one way or another. These were the size scales that these gentlemen were arguing about. Shapley said, okay, well, to account for these nebulae being a part of the Milky Way just has to be bigger than any of us thought it was. That's fine. It's fine. It's just really big. The actual Milky Way size is about a third of what he thought, which being within 1/3 100 years ago is pretty good. Curtis said, these aren't part of the Milky Way, which means not only is the Milky Way smaller than we thought, not only are these other nebulae their own galaxies, they called them island universes back then, not only are they their own galaxies, but they're so small because they're so far away. So the size of the universe in the 1920s to the 1930s, the size of the universe, our understanding went from this big to, I honestly can't tell you how big it is. I don't know. I don't know for sure. We have some guesses, but I don't know. The size scale of our understanding of the world around us jumped from our galaxy to the entire universe within the span of about 10 years. How could we make the jump? How could we say, all righty, Andromeda, for example, who's the closest galaxy to us, that for sure is a galaxy and it's not part of the Milky Way. The biggest extent of the Milky Way was about 300,000 light years. So if somebody was able to measure a distance to Andromeda and it was significantly larger than the largest estimates of the size of the Milky Way, that would end the debate right there. That's another galaxy, has to be. We're not the only galaxy. Oops, the universe is really, really big. So how did they do it? Well, they were looking at the Small Magellanic Cloud. They were looking at those Cepheid variable stars, and they said, hey, we can use a really, really easy trick because that dwarf galaxy is so close to us. We can use a really easy trick with geometry to figure out how far it is. And I'm sure that at least one of you has already seen this trick before, but it is a rite of passage for those learning astronomy. Everybody, take out your index finger, point it up, and extend your arm away from you. Now, without moving your arm, your finger, your head, or your viewing angle, close one of your eyes and look at your finger. And without moving, as best as you can, close the other eye, open the other eye, and keep flipping back and forth between one eye being open and the other eye being open. What do you observe? It looks like it's bouncing. Is it actually physically moving? No, but luckily humans have two sockets for light collection instead of one. So your viewing perspective, as viewed from two different perspectives, will cause the apparent position of something to change. How do we measure that? How do we use that to measure distance? One more time. Put one finger up in front of you. Now put another finger, but have it be closer to your face, much closer to your face. And do the same exact thing. Blink back and forth, but don't change the position of your fingers or your arms. What does the closer finger look like it's doing? It's bouncing more. Closer things, as viewed from two different viewing angles, will look like they're moving more. You see this every day. If you're driving on the freeway, if you look on the ground looks like it's moving a lot faster than the trees in the distance. It's the same exact thing. So we just do that on a much larger scale. We just put that in space. This is the best animation, the best representation that I've been able to find of the phenomenon that you just observed. That phenomenon is called parallax. It is the apparent change in position given two different viewing angles. Now, if we were just on Earth, sure, you could go to the North Pole and the South Pole, make two observations of a star. It may look like it moved, like maybe Alpha Centauri. But you can take advantage of the fact that we're being pulled in a big circle around a gigantic volume of plasma. So as we go around the sun, naturally, over the course of 365.25 days, stars that are closer to us are going to appear to move more for the same exact reason that the finger closer to your face looks like it moved more. And stars that are farther away won't make as big of a jump. And so all we have to do is take a measurement of the position of a star, wait 6 months, take the measurement of the position again. The more it's moved, the closer it is. That's it. It's big, gigantic space trigonometry. I love bringing that up to my astronomy students because most of the astronomy classes that we teach are for non-STEM majors, for them to get their STEM lab credit for their core curriculum. And so they take astronomy, one, because they think it's astrology, and two, because they think it's going to be the easiest one. And so when I pull space trigonometry out from under the rug, it makes them really, really frightened. And it's really funny. Okay. So we conducted parallax measurements on the Small Magellanic Cloud, which means that we measured the absolute distance. That's just geometry. Geometry is true regardless of what you think of it. There is no assumption, there's no model, there is no leap in logic that we have to make to come to the conclusion. That's geometry. We solved a right triangle, that's it. We know the distance to the Small Magellanic Cloud, which means, effectively, that we had the distance to everything in the Small Magellanic Cloud. The distance to it compared to the three-dimensional size of it is negligible. So if you measure the distance to one object that's really far away, you effectively have the distance to everything in that object. It's a nice little shortcut. So we had distances now to every one of those Cepheid variable stars that Henrietta Leavitt was measuring, which means not only did we have their apparent brightness, how bright they appeared to us, we could use their distance and how bright they appeared to us to figure out their intrinsic brightnesses, or what we astronomers call the absolute magnitude. Those Cepheid variable stars behave the same regardless of where we found them. So we found ourselves, by measuring parallax, we found ourselves a little pocket where we can see stars that are pulsating at all different kinds of pulsation periods, and we knew how bright they actually were because we knew how far away they were, which gave us the power to go anywhere else in the universe, and as long as we saw a Cepheid variable star, all we had to do is say, all right, how long is it pulsing for? Go find over here, who is pulsating the same rate? Okay, that's how bright this is, that's how bright that appears. The bigger the difference between those two numbers, the farther that object must be. That is what we call the cosmic distance ladder. That's effectively it. That's the foundation of the distance ladder, and we've been using it for 100 years. There are multiple facilities on this Earth that measure the parallax of stars, nearby stars, to the Earth. The first one that we sent up was called the Hipparcos satellite. That was in the mid to late 90s. And that was in space, orbiting Earth. And it was measuring the apparent change in position and therefore the parallax of about 100,000 stars, the 100,000 closest stars to the sun. Yeah, okay, but then in 2013, we sent up the Gaia satellite, which I believe is the goddess of the Earth. Somebody can check me on that. I think I'm right about that. But that one is farther from the Earth. It's kind of where James Webb is. And it did a little better than 100,000 stars. It measured the parallax angle for 1.3 billion stars closest to the sun. So now effectively we have the absolute distances to about half of the stars through the Milky Way's disk, about half of them, which gives us the power to figure out how far away everything else is. And on the bottom row, Georgia State University specializes in this. Gaia went up and it measured one parallax angle for a couple billion stars. Now you can have one excellent angle made by the best tool that you could ever make. Or you can use a less precise tool, but continuously make the measurement every year over the course of 20 years. We live in a world where we can have both. And so at Georgia State University, we have an army of telescopes on the peaks of the Andes Mountains in Chile. That is a real picture. I don't quite know how it's real, but that's real. And if you zoom in there, here are our telescopes whose sole purpose is to observe the same catalog of stars year after year to continuously provide parallax angles and what we call proper motion. These people perform astrometry, which is astronomy geometry, and it is the precise updating of the measurements of the positions of celestial objects. And so that's just one of the facets that Georgia State University is an expert in. And then in 1924, Hubble takes that parallax measurement of Cepheids in the Small Magellanic Cloud, and then uses the 100-inch Hooker telescope at the Griffith Observatory in Los Angeles and observes Cepheid variable stars in the Andromeda Nebula. He sees the same exact stars doing the same exact things that Henrietta Leavitt saw in the Small Magellanic Cloud, and he compared the period of pulsation to those to the period of pulsation that we have calibrated in the Small Magellanic Cloud. Here's his original result from 1929. These, I believe, are the, let's see, apparent magnitude, these are the brighter ones. Yeah, so these are the Cepheids in the Small Magellanic Cloud put on the same scale as the Cepheids in the Andromeda Galaxy. And so we can compare one to one. We know how bright these are because they're right next to us. Those ones are behaving the same way, but they're a little dimmer. How much dimmer are they? That's your measurement of the distance. Now remember, the largest extent of the Milky Way was on the order of about 100,000 light years for the largest extents, for the people who wanted to keep the Milky Way as the universe. His measurement of the distance using Henrietta Leavitt's results was about 900,000 light years. That ended the Great Debate, which is what we called it. There was no way that that was connected to Milky Way at all. There was no way that even the largest extents could explain how something was connected at a distance of 900,000 light years. What did this mean? Andromeda is not a nebula anymore. It's its own galaxy, 900,000 years away from us, who's a completely different, isolated, unique galaxy. And every other nebula that we've been studying is its own galaxy. The number of objects in the universe that we consider to be the universe went from 1 to, current estimates, 2 trillion galaxies, somewhere around there. So that's not all he did. He's credited with two things, Hubble. One, measuring the distance to Andromeda, and two, the thing that I'm about to tell you. I don't think that he should get credit for measuring the distance to Andromeda because he needed the Cepheids to do it, and he wouldn't have the Cepheids without Henrietta Leavitt. So give the distance to Andromeda and the end of the great debate to Leavitt, but I'll give this next one to Hubble. Hubble, I'm assuming that you all know, his claim to fame is measuring the first measurement of the expansion of the universe. How did he do that? Well, he's got Cepheids for distances, that's great. But the way that we figured out that the universe was expanding was seeing that the farther a galaxy was, the faster that it was moving away from us. How did we initially measure that? Well, I mean, it's the same thing as you standing on the side of a road and hearing a siren go towards you and away from you. It is the Doppler effect, which whenever I have a dog, my wife says that we don't have a dog, but she isn't aware that we're going to have a dog. The dog's name is going to be Doppler, has to be. The Doppler effect is the effect of wavelengths being affected by motion. That's about as simple as I can put it. So if you hear a siren, or if you hear anything, the only reason you're hearing me right now is that my vocal cords are vibrating, causing pockets of air to be dense and then not very dense and dense and then not very dense. And those periods of dense and not dense pockets of air hit your ear, they vibrate your eardrum, and that information tells your brain that you heard something. Sound is a wave, and so it can be affected by the motion of the source of the wave and the thing that made the wave propagate in the first place. So if you hear a siren, that siren isn't doing anything different to cause the waves in the air that it is causing. The only time that you hear something different is when the siren is coming towards you or it's coming away from you. As it's coming towards you, the siren's sound waves all bunch up and get compressed before they start vibrating your eardrum. If you take a sound wave and you decrease the wavelength, you increase its frequency. And if you increase the frequency of a sound wave, you increase its pitch. And so sirens sound high-pitched when they're moving towards you, and the opposite effect happens when they're going away. They sound lower-pitched when they're going away from you. It has nothing to do with distance. Distance just increases the amplitude. It increases the volume of it. The motion is what affects the Doppler shifting. If something is moving faster, that Doppler effect is going to be more. If it's moving faster away, the Doppler effect is going to be more. Photons also behave like waves. You can ask me about particles and waves, about photons, but we can talk about something else that doesn't make me sad to talk about. I'm not a quantum mechanics expert. I'm an astronomer on purpose to get as far away from quantum mechanics as I could. But the way that we have described sound waves, using waves, is the same way that we describe the characteristics and the behavior of photons. And it is very successful. So if a photon behaves like a wave, then the motion of that wave is going to cause Doppler shifting, just like sound waves do. So when we see something and we take a spectrum of it, and so we split all the light up into its components, some of those elements are going to eat some photons and ignore others. If something is coming towards us, all of those waves of light from all those photons are going to get bunched up. And if you start with green, let's say, and shorten the wavelength of green, shifting over to shorter wavelengths of green puts you into blue territory. And if you increase wavelengths starting from green, you go into red territory. So not only does the color, the overall color of things shift towards bluer colors if it's going towards you, and shift towards redder colors if it's going away from you, the signatures of light being eaten by different elements, these different lines, we call them absorption lines, these absorption lines will hop to a larger wavelength the farther the galaxy is moving away, simply because those light waves are getting expanded and those wavelengths are increasing simply due to the motion of something away from us. We call it red shifting. And so we took spectra of a bunch of different galaxies, and Hubble noticed that if a galaxy had a farther distance, the redshift would be larger. It would be moving faster away from us. The wavelengths of all of these absorption lines would be longer and longer and longer the farther the distance was. Here's his original plot from 1929. The velocity, or the redshift, of galaxies is on the y-axis. So faster galaxies moving away is higher on the y-axis. Distance on the x-axis. Black points are individual galaxies. Open points are groups of galaxies. This black line is a best fit to the black data points. The dashed line is a best fit to the open data points. Both curves tell you the same thing. They might have different slopes, but the relationship is still the same. What is the relationship? farther galaxies are moving faster in every direction. How do you explain that? The universe is expanding. What do I mean by that? I mean that the fabric of the universe is increasing in volume as a function of time. That's what I'm saying. So it's not that every galaxy has an Acme rocket that's firing away at every other galaxy. It's that the amount of asphalt between us and every other galaxy is increasing in length without us having to do anything. The slope of this line, the slope of any line will tell you the rate of change of whatever you're plotting, right? The slope of this line is the rate of change of the speed of galaxies receding from us as a function of their distance. In other words, the slope of this line is a measurement of the expansion rate of the universe. So if you have good distances and you have good velocities and you have a good fitting algorithm, the slope of this line will provide you a measurement of how fast the universe is expanding. His original measurement almost 100 years ago was 500 kilometers per second per megaparsec. A parsec is just over 3 light years. The mega prefix stands for million. And so we're talking about a galaxy will be moving at a speed of 500 kilometers per second away from us if we walk 1 million light years into the universe, and 1,000 kilometers per second if we walk 2 million light years into the universe, and so on and so on and so on. It provides us with a rate of change of the universe. And this was the first measurement. We call this slope H naught, H for Hubble, and naught standing for the first time that we measured this. Then we kept doing that from the 20s up until now. We're still doing it. There's so much money that has been poured into trying to measure this one number. It's kind of silly. So what is this? This is a graph of the continual updating of the measurement of H naught, the expansion of the universe, as a function of time from the 1920s up until the 2010s. So can you tell where we got our shit together? What was going on here? There were a couple of dates. First off, right there, you can see that the H naught value took a tumble, and that's because in the mid-50s, Walter Bode, I think I pronounced that name right, he figures out that there's different types of Cepheids. There's subclasses of Cepheids, and if you were to split Cepheids into their different subclasses, they would follow slightly different relationships between their period of pulsation and their luminosity. And so if you correct for that, you get pulled one way or another for distances, and so that affected the slope of the line. And then, come on. There you go. And then in 1956, Alan Sandage, who did a lot of cataloging for us back then, he figured out, hey, sometimes these Cepheids that we're looking at in other objects, sometimes it's not one Cepheid that we're looking at, sometimes it's a couple of Cepheids that are all packed together, and really far away it looks like they're the same object. And so the period that you're getting from measuring how the light changes, it will get confused if you have more than one thing there. This is an example of how we're doing this nowadays. This is a field of Cepheids in a galaxy that's probably some tens of millions of light years away. And that's an observation from the Hubble Space Telescope up there. If the James Webb Space Telescope looks at the same star field, that's what it sees. That's what $10 billion of your taxpayer money gets you. Really, really precise observations of stars. And then finally, from the 50s until the 90s, we try a bunch of different things, and effectively the measurements of H naught from the distance ladder bounced between 50 and 100 kilometers per second per megaparsec. Meanwhile, has anybody in this room watched any of the Avengers movies? I wouldn't be surprised if the answer was no. But there was something silly that happened in the last really big one, the last one that was actually profitable. All of the heroes lost in the movie that came before it, and then the movie opens and all the heroes are just kind of lounging about, no one knows what to do. And then a rat stumbles on a button that releases this guy from whatever he was trapped in, I don't remember. So if that rat didn't do that, the entire movie wouldn't happen. Like the whole, like, oh, they bring back everybody who died and they save the world again and they defeat the bad guy, whatever, wouldn't have happened if a random rat didn't walk across a random button in a random place on a random call. That same kind of thing happened to us, except it wasn't a rat, it was pigeons and it was poop. I see. I'm so honest about this. If you're curious, there's probably a whole host of articles written about this. But the desperate attempt to try and get rid of pigeon poop led to the awarding of a Nobel Prize for the discovery of the cosmic microwave background radiation. These guys, the ones on the right specifically, these guys, Penzias and Wilson, they were trying to observe with their radio antenna for a galaxy. I think they were observing some galaxy in the radio, and they kept hearing static. No matter where they pointed, no matter if it was day or night, which in radio, it doesn't matter. The wavelengths are so long, it doesn't matter if you can observe day or night. You could observe through clouds if you wanted to. But they kept hearing static, like some low level of flux that was coming through their receivers, and they couldn't figure out what it was. And so they cleaned up everything. They got leaves out of their antennas, and they got all this stuff. They pressure washed it, and then they're like, pigeons nest up there all the time. And so they went up there, the two of them, and they cleaned off all the poop, and they came back and they still heard the static. What they were hearing was the faint radiation from the first ever photons produced 300,000 years after the Big Bang, the cosmic microwave background radiation. And so that observation led to them winning the Nobel Prize in physics in 1978. This is one of my favorite things that's real. So what do I mean by the first photons that were ever produced? Neither me nor any physicist worth their salt should tell you with any sort of weight or certainty what happened in the instant of the Big Bang or anything that happened before the instant of the Big Bang. Our theory, the standard cosmological model, or the Big Bang theory, commonly, that thing explains everything up until the instant of the Big Bang. I can describe to you the next instant up until today after the Big Bang with our theory, but it does not have the language that can describe the instant of the Big Bang. Go off into the world, if somebody's saying that they're a kook, don't listen to them, okay? And we have to be very careful about how we use our models, which have assumptions, to make claims about the universe that we haven't directly observed. Also, our standard model of cosmology says that 5% of the universe is luminous, the energy budget, and then 25% of it is dark matter, which we've never observed and don't know is real, and dark energy, which we've never observed and don't know is real. So the Big Bang theory, 95% of the energy budget, so it says, is something that we've never seen and don't know how to detect. That's a big assumption to start making grand claims about the universe on. So if that is all true, what was it like in the instant after the Big Bang? Kind of like summers in Atlanta, actually. Actually, I taught at Troy University for 2 years, and it's worse down there because it's closer to the Panhandle. Like, I swam to work a few times, it felt like. So, if that's all real, what happened? Well, take all matter in the universe, because energy can neither be created nor destroyed. Take everything that exists in the universe and then compress it down into one single point. If you compress a gas, you increase the temperature. And so the Big Bang, the material was hot. In fact, it was ionized, completely ionized plasma. Ionized meaning all the electrons, no electron was attached to any atom at all. Which means that there was no process for photons to travel freely through this. This is kind of a visualization of what this looked like. But what would you see? Next to nothing. Because the only reason you're seeing anything in this room is that a photon was able to reflect off of a surface and enter through your retina, enter through your lens and your pupil and then hit your retina. In the early universe, every electron was freely roaming around, disconnected from any atoms, which means that any photon that happened to be floating there, the electrons snatched it up and took it. So photons were not freely traveling anywhere. The early universe was opaque. This is a plot of energy density. It is places where there was more energy or a slightly hotter location, and then less energy, a slightly less dense region. These are not photons. There would be nothing to see because no photon is able to get anywhere before being immediately eaten by an electron, because everything is ionized because the temperature is so high. As the universe expanded, the temperature cooled down, but everything is still moving really, really, really fast. So it took the universe expanding and cooling for approximately 300,000 years before the temperature was low enough, meaning that particles were moving at a slow enough speed for an electron to attach to an atom and stay there instead of having enough energy to immediately leave the atom once it was connected. Once all those electrons were connected to their atoms, they started to ignore the photons, and so the photons were able finally to freely move about in space, reflect off of things, and finally be detected by whatever, as soon as electrons were able to attach back to their atoms. So those photons, the ones that were the first ones that weren't immediately being eaten, the first free traveling photons that the universe was ever able to produce, those photons were generated at a temperature that would make those photons glow in the infrared. So they wouldn't be visible to us because our eyes can only detect optical. They can't detect UV. They can't detect infrared. But if we had infrared goggles, this is what the universe would look like. And then 300,000 years after the Big Bang until 13.8 billion years after the Big Bang, which is where we are today, those photons were redshifted by the universe for 13.8 billion years. And so the original infrared photons, the infrared wavelength, that got stretched by the Doppler effect all the way to the microwave regime of the electromagnetic spectrum. And so because we humans have popped up 13.8 billion years after the Big Bang, when we look up, we see those photons redshifted into the microwave. If we popped up earlier, we might see them, in the, no, microwave is right below infrared. We might even see them in the infrared. Who knows? There's a lot of wavelengths in the infrared. So we theorized about this for decades. And then we finally, at the end of the 80s and in the 90s, we sent up the first satellite whose job it was to try and detect the cosmic microwave background radiation. The first one to do it was the Cosmic Background Explorer, or COBE. This is an artist's rendition of what it looked like. What it did is it took a panorama of the entire sky. So imagine taking your phone and then spinning around like this, and then taking all that data and then flattening it out into, kind of like taking the world and then flattening it out into a weird ovular shape. And its job was to detect the areas of higher temperature and lower temperature. And because we were detecting the early plasma, higher temperature means that those locations would be slightly denser regions of the early universe, and places that were slightly colder would be places that were slightly less dense in the universe. This is what COBE saw. This is the first observation of the panorama of the cosmic microwave background radiation and its temperature fluctuations. And so I hope this is colored correctly. Red, blue is hot, red is not. So blue would be slightly denser regions and slightly higher temperatures, and red, slightly lower temperatures, slightly less dense regions. We didn't know what this would look like until we took an image of it. What does this tell us? The early universe was not uniform. If it was, it would all be one color. It wasn't. The distribution of matter in the early universe was ever so slightly non-uniform, which paved the way, those slightly overdense regions, the overdensity would cause those regions to have a larger gravitational pull, which means over longer periods of time, those locations, which would get bigger through expansion of the universe, would pull in more matter than surrounding environments, which means these slightly denser regions in this map would eventually evolve into the locations of galaxy clusters and galaxy superclusters. Or so we think. Sounds pretty cool though, doesn't it? The next one was in the early 2000s, my favorite era. I was born in 1995. I was born in the wrong era. I wanted to be an adult in the early 2000s. WMAP, the Wilkinson Microwave Anisotropy Probe. Anisotropy? Anisotropy. The non-uniformity probe. It had better equipment, better cameras, better detector, higher fidelity. This is what WMAP saw. The CMB, but now at higher resolution because it cost more money and the equipment was better. So what is this showing us? Again, the early universe is non-uniform. This is the distribution of temperature of the first photons that were ever able to travel in the universe's lifetime. This, cold region, hot region, hot region, hot region, cold region, cold region, cold region. Meanwhile, I know, what does that have to do with the expansion of the universe? Just wait. Meanwhile, we're getting really, really good at measuring the slope of these, what we call Hubble diagrams. Why? Well, because we've trained a bunch of telescopes and we've generated a bunch of careers, including my own, to measuring the best distances to as many galaxies as possible using as many telescopes around the world as possible. So this is a result that was published in 2001, right when WMAP was making its observations of the cosmic microwave background. This is the same kind of plot that I've shown you before. Recessional velocity or redshift is on the y-axis, fastest galaxies, slowest galaxies. Distance is here, close galaxies, far galaxies. This result was part of the Hubble Space Telescope Key project, where we initiated this entire campaign to observe more Cepheids than we ever had in more galaxies than we ever had with the best equipment that we've ever had with the Hubble Space Telescope. After it got its contact lenses after the early 90s, after we sent it up and it couldn't see anything. So they plotted a couple of different values of the slope of H0. The dotted ones are just examples of if we chose higher values or lower values. The one in the middle, 72, is the best fit. This is the residual, where data points minus the value of the line at that point is shown here. So the more that they scatter around the horizontal line, the more that they agree. So in 2001, based off of observing Cepheids, so very little assumptions, basically objective data, as much objective data as possible. The best H0 that we had in 2001 was 72 plus or minus 8 kilometers per second per megaparsec. How did we get that data? How good did we get? How good were we in 2001 to 2010? Well, let me just show you how many galaxies we've measured the distance for and what we can do with those after we've measured the distance. So this is going to be a plot, a three-dimensional plot of the positions of galaxies and their distances. This is a simulation, but it's showing you real data. So what this is about to show you is the actual three-dimensional distribution of galaxies around the Milky Way due to us measuring distances from the distance ladder. Every point is a single galaxy. And if you zoom out far enough, you find the galaxy supercluster that the Milky Way is a member of, Laniakea, Hawaiian for immense heaven, and Hawaiian because lots and lots of telescopes that are trained on the distance ladder research are on the mountaintops of Mauna Kea in Hawaii, the Keck telescope specifically. This is a map of all those galaxies. This is tens of thousands of galaxies all around the Milky Way galaxy. So this is X, Y, and Z, so it's going to spin around. This is a three-dimensional volume. It's not that there are no galaxies here. It's just that we're in the center of our map, and this is the disk of the Milky Way. Like, we can't see things if we look through the disk of the Milky Way. It's kind of like trying to see the sun if it's cloudy outside. You can't, right? Because there's stuff in the way. So it's not that nothing's here. It's just that we can't see it. These are all their positions, and their positions are given by distances that have been measured by scientists using the distance ladder. And we can measure how far they are away. How fast they're moving away via the Doppler effect. So we can show you which one of these galaxies are moving towards us and which ones are moving away from us by plotting arrows, where blue arrows are going to represent blue shifted galaxies and red arrows are going to represent red shifted galaxies. Now let's take away expansion. Let's leave the only motion here to be gravity. The only things that are making things move towards us and away from us. Expansion's making everything move away. Take away expansion. Those we call cosmic flow lines. These lines represent the velocity of galaxies solely generated by gravitational interactions between galaxies and other galaxies. If the universe wasn't expanding, these are where galaxies would be moving or flowing through the cosmos, or cosmic flows. I just love the name so much. Now, we've done this for our entire supercluster, which means that we have the directional flow of the entire gravitational field of the Laniakea supercluster. What does that look like? Welcome to the basins of attraction, where the red locations are where cosmic flow lines are converging, meaning everything is being pulled into these locations. And the blue parts are where galaxies are receding. They are being pulled away from those regions into what we call the great attractor. which is this guy. So each of these lines and these arrows represent where galaxies are being pulled. And we only know this because we've been able to remove expansion. And the only way that we've been able to remove expansion is by measuring H naught in the best way that we can. And this is the same map, it's just a different angle. We are being pulled out of the Virgo cluster. In fact, we're moving with the Virgo cluster into the Great Attractor. These are some of the most recent results of Hubble Space Telescope calibrations of Leavitt's law. We're still using it today because there ain't nothing better. Take my word for it. Trust me, I'm a scientist. These on the right, I'm sorry, on the left, apparent magnitude and period of pulsation. So these are Leavitt's law for different filters on the Hubble Space Telescope. Every one of these dots is a star, and they're different brightnesses because if you look in different wavelengths, things will be brighter and dimmer depending on what they're made of. So these relationships have shown the smallest scatter for any calibration that we've had for these things, where it's so tightly correlated that these things produce the distances with the smallest uncertainties effectively in extragalactic astronomy. On the right-hand side is the uncertainty on the measurement of H naught. So the uncertainty in all the slopes that we've been measuring with our best equipment. And on the x-axis is years, where this was 2001 for the Hubble Space Telescope Key project, and then this is 2019. The error has gone from 5% from the distance ladder down to what we currently have it at, which is effectively 1%. We are so confident in how we are measuring H naught by measuring the slopes of all those Hubble diagrams. Our distances are so great, we know what the Doppler effect is doing, and so there is only a 1% uncertainty nowadays on our measurement from the distance ladder of the expansion rate of the universe. Meanwhile, we return to the cosmic microwave background. And I'm about to tell you why this is going to be a major player in the expansion debate. But now we've sent up the guy that's going to end everything. This is our last resort. This is Planck. Planck observes the cosmic microwave background at the highest resolution ever before from 2009 to 2013. And in 2013, it releases its map, the highest resolution observations of the first photons ever produced. This is what Planck saw. This is the most detailed map of the cosmic microwave background that we have. Here's how they made it. And so it continuously sweeps the sky, stitching together panorama after panorama after panorama, and then flattens it out like we do with world maps. Removes all the frequencies that we know aren't coming from these photons, and we're left with only the radiation coming from the oldest photons that have been traveling the farthest distances in the universe. From Kobe to WMAP to Planck. The amount of time, people, and money that went into taking the observation from this to this is striking. And it is above my pay grade, that's for sure. This won the Nobel Prize also. This is the main result. This is the Planck measurements of the temperature fluctuations. So if you were to imagine you taking the entire map of the cosmic microwave background and then running a scanner over it and say, hey, when do you detect spikes in temperature? When do you detect lulls in temperature? Then say, okay, at what scale do we find the most amount of fluctuations? Is it if we zoom all the way out, do things look really different? Or when we zoom out, things look fine, things look the same. But if we zoom all the way in to very, very small pieces, that's where we see all of the different fluctuations. At what scale is the distribution of matter different? So on the y-axis, it's how much the temperature is fluctuating. On the x-axis, it's scale, where this is the smallest scales, slightly larger scales, even larger, even larger. Kind of hard to picture. Luckily, the European Space Agency has videos that I'm able to steal. Power spectrum just means plot temperature as it changes. So this smallest scales, if you zoom all the way in, things are sort of different, but if you were to, put one horizontal line through it, it would kind of do an okay job representing what everything's doing. If you zoom out a little bit, I mean, sure, there's little peaks and valleys, but the difference generally is not that much. Over here, oh, I'm sorry, the scale is getting smaller. Largest scale, smallest. I don't know why they did this backwards. Ugh. Smaller and smaller. If you go even smaller, you see even more differences. If you go even smaller and even smaller, you find that there are differences in the distribution of matter, even on the size scales of individual atoms. Because at this point, there weren't any molecules. There was hydrogen, helium, a light seasoning of lithium, and that's about it. So what is this graph? It is a display of how the distribution of matter in the universe varied on different size scales. It is an all-encompassing measurement of how the distribution looks at any scale. So it's all information contained within one plot. So why does that tell us anything about the expansion of the universe? It's because the cosmic microwave background radiation is the farthest back data that we can ever detect. We're not detecting anything before that. The only things that we can detect as astronomers in the universe is photons, neutrinos, and gravitational waves. That's it. We're not detecting gravitational waves from the cosmic microwave background. That ain't happening. We can do it with black holes. We're not doing it with the cosmic microwave background. So we use that data, which is the first and like farthest back data that we can, and we say, okay, that's prime material to throw against our model of the universe. Our model of the Big Bang is a toy in a computer. It's a toy of the universe in a computer, and there are different knobs that we can turn. So we turn one knob, we change the geometry. If we turn another knob, we change the amount of matter in the universe. If we change one knob, we change the amount of dark energy in the universe. And if we change one knob, we can change how fast the universe expands. Now, why would that be connected to the cosmic microwave background? It's because our model of the Big Bang produces a CMB of its own, and then expands and shows us what it thinks the distribution of galaxies are nowadays. We didn't have something to compare its cosmic microwave background radiation to before we measured it with Planck and with WMAP and with COBE. So we said, okay, here's the cosmic microwave background. Here's all of the what we call free parameters. How many knobs do you want to set? If you want 5 knobs, okay. Well, then you're telling me that you only need 5 different knobs to make something that looks realistic. Okay, so how about 10 knobs? How about 20 knobs? Whatever. You can tune those knobs to anything. You can make the universe expand at the speed of light. You can make it not expand, whatever. But there's only a set of values that you can choose to make a realistic universe. Is that making sense to everybody so far? Okay. We can create these simulations in supercomputers. So this is a large simulation of millions and millions and millions of light years right after the Big Bang. And particles will move under the influence of our laws of physics and our free parameters to the standard model of cosmology or the Big Bang theory. So you can see that these are galaxy clusters at this scale. You can see clustering, you can see that cosmic web start forming, but the initial position and the rate at which galaxies fall in depends on what we've chosen to set as the expansion rate in our simulation. If we set it to 67, which is what Planck found, then the universe starts expanding at a rate, and gravity has its strength, and its strength doesn't depend on the expansion rate. And so the amount of clustering that occurs, how easy it is for galaxies to pull on each other in the early universe, is completely dependent on how fast the expansion is taking them away from each other. If you make the universe expand more, galaxies have less time to cluster. And so you won't get as thick of a web as you see here. If you make the universe expand slower, then you give galaxies more time to cluster, and so you get a denser web. So the expansion rates can be inferred by models to the CMB, because it says, okay, here's the CMB, here's the cosmic microwave background. Set your parameters so that your toy model of the universe produces this cosmic microwave background that we've observed. Then it's all right, well, I have to set this knob to this, and this knob to this, and this knob to this. Okay, what expansion rate did you have to set your knob to so that the simulation of the universe looked as much like the cosmic microwave background that we've observed as possible? The answer was 67 kilometers per second per megaparsec. And that number has stuck ever since 2013. Now, 67 and 72 don't sound like they're that different from one another, I grant you that. However, each of these measurements has an uncertainty, meaning, like if this is a measurement here, these are the error bars. That means effectively, this measurement can be anywhere defined between these two boundaries. So the shorter the error bar is, the more precision that I'm telling you that I have. I don't know what value it is in here, but I know it's nothing here, and I know it's nothing here. It's contained in here. This one, I'm even more precise about it because it's contained within a smaller error bar. The problem with the expansion rates that are found to models to the CMB, where you set a knob, and if you find the right number, it reproduces the data, all of those values found by models are all smaller and do not agree with all of the values of H0 that we're finding from objective measurements from the cosmic microwave background. And the problem with us getting better and better at both of these branches, both options of measuring the expansion rate, we're getting better at both of them, and the values are getting farther away, and the error bars are shrinking. So not only are they disagreeing more, the gray area between them is disagreeing more as well. In 2024, this is the most updated value of H0 that we have so far. James Webb is working on new calibrations right now, but what we have right now is H0 is 73 and some change kilometers per second per megaparsec. From Planck, it's 67 with a tiny error bar. Those things don't overlap. They don't agree. If we compare which H0 that we have to choose to then look at the basins of attraction, the basins of attraction, how galaxies are moving, that depends on gravity, but it also depends on how quickly the universe is expanding. The universe's expansion rate should get larger the farther away we look, because galaxies are moving faster the farther that we look. That doesn't happen if we choose H0s that are closer to Planck, because that makes things move faster due to gravity the farther that we look. And that doesn't really make any sense. That's not really an objective measure. That's just saying, well, we're seeing how everything is behaving, and things don't behave that way if we choose a really slow expansion rate. It only happens that way if we choose a fast expansion rate. What's going on? We're not very sure. We're not very sure. But we are sure that it's not a problem with how we understand Cepheids, and it's not a problem with our tools. Because what this is Leavitt's law. So this is brightness as a function of period of pulsation. All of these different circles are different Cepheid stars. And this is a comparison between calibrations of the Hubble Space Telescope and calibrations of the James Webb Space Telescope. So the grayed out points are the distribution of Hubble. You can see there is still a linear correlation there, but there's some scatter. There's some points that are above the line. There's some points that are beneath the line. That's not because Hubble has a hard time seeing them. It's because with Hubble's resolution and the size of its mirror, when it sees star fields that are a little crowded, it's hard to separate star from star. James Webb doesn't have that problem. For the same star, this is what James Webb sees. These red points are the same Cepheids, but they're observed by the James Webb Space Telescope. We've never been better at measuring distances to Cepheids, is what I'm trying to tell you. And I'm also trying to tell you that we spent your money really well. Here's the best way that I can visualize this. This is from 2000 to 2025. This is the value of H0. The blue points are from the cosmic distance ladder. The red points are from Planck and models to the cosmic microwave background. They have disagreed more, and the uncertainties have shrunk as time has gone on. And because the uncertainties have shrunk, we're able to perform we're able to perform statistics. The values within the uncertainties are 5.3 standard deviations apart from one another. Statistics tells us that that's equivalent to it being a 1 in 3.5 million chance that this disagreement between measurements of H naught, which we call the Hubble tension, there's a 1 in millions of chance that it's just statistics, that it's just random, which means there's a fundamental thing going on here that we do not understand. What is the Hubble tension, and what are the questions? Is the Big Bang theory, is the standard model of cosmology incomplete? Are our distance techniques wrong? Have we fundamentally misunderstood the relationships between our distance markers? Or have we fundamentally misunderstood the set of functions that we've chosen to best represent how the universe evolves and changes? I don't know. Which is good, because then I can still have a job and people will pay me to figure out the answer. So this is one of the largest contentions in extragalactic astronomy. One of the main reasons that we used as justification for funding for the James Webb Space Telescope was to explore and try to find the answer to this problem. So what is James Webb doing right now? What are scientists like me doing right now? We're refining and trying to extend the cosmic distance ladder so that we can provide measurements of the expansion rate using the largest set of distances to the farthest things that we've ever seen before, and see if we start seeing different things. Is the universe's expansion rate constant? I don't know. Would it be different in the early universe than now? I don't know. One person asked one of the founders of one of the distance ladder techniques, his name is Brent Tully, he gave a presentation on the basins of attraction, and someone said, what if there was different expansion rates in different locations of the present day universe? And he goes, oh, you mean like different Hubble bubbles? Sure, why not? I don't know. We're able to test that one, but I don't know. The dark energy survey is finding that the cosmological constant may not be constant either. So I think that the universe is telling us that we have a lot more work to do, but luckily we've got some pretty good telescopes and some pretty good universities, not that I'm biased, to help us out. So I will be happy to take any of your questions, and I look forward to lunch. But for right now, I'll just say thank you very much for your time and your attention. Sure. Oh yeah, it's so much fun. Oh yeah, there is so much politics. There's so much petty debates going on between the two camps. Yeah. Luckily, I've found myself to be in a group of scientists who are like, well, one of the answers is right, so why not we just make them both as good as we can and then talk about it later. But there are people who are like, die hard, the Big Bang Theory is correct people. And then there are other people who are like, we understand Cepheids. I don't know what you're doing in cosmic microwave background land, but we understand how stars work, so it's not us. I'm kind of in that camp too, but yeah. That's a fantastic question. And that is because in order to use our standard model, our toy in our computer, the only way that we make a realistic universe in the computer is modeling the universe as though it was just the surface of a balloon, an expanding balloon. Not the interior volume, not the exterior volume. So imagine you are only confined to walk in the surface, in the little lip. So there are things that I can think of, but I'm an observational astronomer, right? So what's outside the universe? I don't know. There's no way for me to measure that, so I don't know. I find it to be more probable that this universe ain't the only one. So what's outside of it? I don't know. It would seem less surprising to me that the universe was hanging around with other universes in a multiverse setup. Where what's outside the universe? Well, it would be a dimension higher than ours, right? Going from a flat piece of paper to the z-axis, something like that. Yeah. This is my job. Yeah. Yeah. What is a galaxy? A galaxy is a location where a bunch of stars, gas, and dust have come together. That's about it. So at most locations in the universe, you don't find those conditions. And so it had to have been a location that had a large enough gravitational pull that it was able to collect all of those things in the first place. And anything you collect a bunch of things in a small volume, they all start spinning around each other. And if you make things spin on different sized ellipses at different distances, you'll create a bunch of spiral patterns. There's a word that you should tell your grandkids, though, and it's my favorite word in astronomy: flocculent. Flocculent is a description for the morphology of galaxies. And it looks like this. It's like fluffy, like feathery. So if the spiral arms are so close together and there's a lot of gas and dust, it doesn't look like there's any breaks in the spiral arms. And so it looks like when a bird tucks in their wings, right? You can't see, there's so many feathers stacked on top of one another. Flocculent. It's my favorite thing. Of course. Thank you all. Thank you.